Hey folks, welcome to this lesson on kinetic molecular theory. So when we look at the periodic table at room temperature being 25 degrees Celsius as we have here, we have a few elements that are in gases, and that's denoted by red. We also have the bulk of them in this blue color, which is solid, and we have two, bromine and mercury, in the liquid state. So what we're going to be looking at first is looking at the states of matter and also trying to apply a new theory called the kinetic molecular theory to why these different states exist as they do. So when we look at the states of matter, we have solid, liquid, gas, we have plasma, and we also have some other states that we're not going to be looking at right now. And you've probably seen this before when we were looking at grade 9. When you go from a solid to a liquid, it's melting. If you go from a gas to a liquid, it's condensation, for example, ionization, deionization. But when we look at this, we can start taking this and breaking this down a little bit. And when we look at a solid, we know that it has a definite shape and a volume. If you think about it like an ice cube, and you kind of keep it in that kind of freezing temperature, it's going to keep its shape and it's also going to keep its volume. However, when we look at water, for example, it takes the shape of a container. If we put it into a square container or a round container, it will take that shape, but it also has a definite volume, which is why we use it for things like brakes. If we try to compress it, then it's very, very, very slightly compressible, but what we do is we pretty much call it incompressible. And gas, it takes the shape of the container, so if we let gas into a room, it would take the shape of the room, but it also has an indefinite or a volume, or it takes the volume of the container. So we put it into whatever, it can expand, it can contract, unlike liquids and solids. One thing that gases and liquids have in common is that it's a fluid, and we're going to be talking about that in a little bit. But when we look at compressibility, again, solids, if we try to compress a solid, it's very incompressible. Same thing with liquids, very, very incompressible, only slightly. And it also depends on the type of liquid that we're talking about. But gases, they're very compressible. We can have a gas as 1 liter filling up a room, or we can put 1 liter into a little bit of a bottle that basically is 1 liter of volume. So it's compressible. We can kind of push it to take up all that little empty space in between and make it into a smaller volume. Low density, and we're going to talk about that in a little bit next video, is when we think about density, it's mass over volume. And because there's so much space in between these gas particles, the volume is huge, therefore the density is small. Unlike a solid which has high density, the volume is pretty small for the amount of particles that are in there and it has a higher density than a gas. And then we look at our molecules. Because there's a little bit more empty space, these molecules are found farther apart. So when we look at the behavior of matter, we try to use this kinetic molecular theory to explain this. And it does a pretty decent job. And when we look at this, it's all about the attractions between the atoms or the particles or the forces that act between them. And as we know, these are our intermolecular forces. So we said London dispersion forces, dipole, ion dipole, etc., etc. So when we look at these things, we have to look at the forces between them to kind of give us an idea of how they're going to behave. Now, in a solid, because they're very, very close together, they're actually going to have very, very strong forces between one another. And they also don't have the amount of energy to escape those forces. If they did, they'd actually act as a gas. So these particles they have very, very low kinetic energy. They don't have, and kinetic energy is the energy of motion, they don't have enough energy to actually move out of the state of being a solid. So we call them as they having vibrational energy, where they kind of move back and forth and they vibrate in space, but they don't really move too much out of that original location. When we look at liquids, they have a little bit of a higher kinetic energy. So that means that maybe they're, and we can think about it, this is ice, where this is ice and this is liquid water and then gas vapor. How do we get to these different states? We add energy. And we add energy to go here from ice into a liquid water into a gas. And so if we add energy, that translates into a higher kinetic energy. So these particles, these molecules, can actually start moving and sliding over one another. And because of that, they actually have weaker forces. Why do they have weaker forces? Well, because they have more energy to able to escape those forces and slide past one another. So they have translational and vibrational energy, so they can kind of move in a different way, and we'll see that in a second. If we add even more energy into this liquid, we can get it to completely move apart from one another. You can see that there's only one molecule or one particle in this whole area. because it actually has so much kinetic energy that it can actually break from the forces that keep these particles together. So when we look at there's a certain amount of forces that are being broken and formed and broken and formed that allows them for sliding. When we look at here, these intermolecular forces that are between these individual atoms are kept pretty much where they are. So as we add energy, we're translating that into kinetic energy, and it can escape these forces that keep these particles together. And so they have a lot of different energies as well: rotational, translational, and vibrational energy. So when we look at different types of kinetic energies, again, vibrational, rotational, translational. Vibrational is in a number of different ways. They can kind of stretch. So both these bonds can stretch symmetrically, or one can stretch more than the other, that's asymmetric, or they can kind of bend back and forth. These bonds can go this way. So this is vibrational motion. Rotational is it can turn this way, or it can turn this way, or it can turn that way. So it's talking about just kind of rotating around a central axis. And translational means it can move forward. So when we look at gases that have translational, rotational, and vibrational, it's moving forward at the same time it might be spinning, and at the same time these bonds might be stretching and giving on one side or the other. So when we look at this kinetic molecular theory only applies for something called an ideal gas. Now, the key thing to remember is that an ideal gas does not exist. It's an imaginary gas that fits these assumptions that we make. And the reason that we've created this ideal gas is because it actually makes our lives a lot easier when it comes to calculation of gases. And what people have found is that there are some gases that behave nearly ideally in certain conditions. Once you start changing conditions, they can actually start changing the way they behave, for conditions being pressure and temperature, for example. But if we take those things away and we keep them at a certain condition, we can make certain assumptions that make our lives a lot easier in terms of calculations. And so this kinetic molecular theory is based on 5 assumptions. Now these assumptions are, number 1, gases consist of a large number of tiny particles that are very, very far apart relative to their size. So if we had a gas particle the size of this dot here, then the next one would be maybe over here. That's a pretty big distance relative to its size. We could probably fit a number of little gas particles over in between, so the space between them is relatively big. Collisions between gas particles and other particles, also collisions against the wall of the container, are perfectly elastic collisions, which means that if we have one thing going, it bounces off the other. So if we had a wall over here and we had one particle, we could see that when this particle goes, it's going to bounce off the wall completely, and all of this energy that originally had here is going to be kept over here. Now, if there's a particle that's going in one direction over here, and let's say we had a stationary particle that is there, once this original particle hit the stationary one, well, all of the energy would be transferred and it would rebound a different way, or keep going that way. So gas particles are also in continuous rapid motion, which means that they possess kinetic energy. So if you had a stationary molecule that didn't really move, it really doesn't have any kinetic energy because it's not moving. What we're assuming is that all these things are moving around and they're constantly rotating or translating or whatnot, and they're always moving in some kind of direction. They're very random. So if we had this, we bounce off that way, bounce off here. If we're kind of looking at the lines as being our guides, so here, so they would just be in constant random motion, going and bouncing throughout. One of the key things is that they don't have any forces of attraction or repulsion. Now, again, we're talking about an ideal gas. In real life, gases do have attraction and repulsion. Remember that the intermolecular force that's found between all of things, there's the London dispersion forces. So of course there would be attraction or repulsion if we're talking about two nuclei getting together. But in the realm of an ideal gas, they have no forces. And again, the average kinetic energy of a gas particle depends on the temperature of the gas. If we increase temperature, we increase kinetic energy. So we can look at this kind of pool table as an ideal or an analogy of the kinetic molecular theory. If we kind of broke this set here, we'd see that all of these balls would move in a random motion. Now, it's very hard to talk about temperature and more kinetic energy, but let's say that these balls just kept going, moving along. Well, if we increased our energy, as we saw in a couple slides before, we increased the energy that they would move in, and so they would start moving a little bit faster and faster. And if we kept adding more and more energy, they would move faster and faster. Now, when it comes to the attractive forces, think about it this way. If we hit a ball off the ledge of the pool table, there's not an attractive force, that we can see. It bounces off elastically and keeps moving forward. If we had two balls, let's say this one over here was moving here in a straight line, and this one was moving past it, what that would look like if they had no attractive energies is that they would just keep moving forward. But in real life, what would happen is if this ball was moving forward and this ball would be moving this way, they would actually start to curve a little bit based on the attractive forces they would have for one another. But again, in an ideal gas or the kinetic molecular theory, we're assuming that those attractive forces or repelling forces are non-existent. And finally, if they collide with one another, it's like a perfectly elastic condition, so all the kinetic energy is transferred. So if we had one ball hit to another one, there would be a transfer of kinetic energy. Now, once again, this KMT only applies to ideal gases, and ideal gases do not actually exist. You can see by here there's a little bit of comparison between a real gas and an ideal gas. Some do behave very ideally, as they say, but there is some deviation as to what their behavior is actually like. And then it also depends on the conditions, pressure, and temperature, namely. So remember that keep that in the back of your mind, that they don't actually exist, but some of them do act very, very similarly. Because of this, it makes our lives a lot easier. Thanks very much for watching. See you soon.